to celebrate the 200th anniversary of the Regent's Canal. We shan't just be looking at Limehouse this evening. We'll be visiting other places in Britain and elsewhere in the world. On this opening slide, I've taken the liberty of using the lovely memorial plaque that was produced by actually Denise Kerr of St Pancras Cruising Club to celebrate their anniversary cruise, which they had from St Pancras Cruising Club down to Limehouse just a couple of weeks ago. Further than many of our Cruising Association members have been this year. So congratulations to St Pancras, and I'm very happy to acknowledge them. Also very happy to put in a plug, I'm not being paid extra for this, but to put in a plug for the London Canal Museum, and I'd warmly recommend a visit to it. I'll let Martin at the end just confirm the current opening times, but if you've not been before, I thoroughly recommend the Canal Museum, just near King's Cross St Pancras Station. See inside a narrowboat cabin, peer down into huge ice wells, learn about horses, boats, cargoes, and how the horse was replaced with engines in boats and tractors on the towpath. I'm reading from the official spiel, in a fine Victorian building built as an ice warehouse. So I thoroughly recommend a visit there. But we're going to begin neither there nor at Limehouse, but here, about a mile from Limehouse, at Tower Hamlets Cemetery Park. Not to be confused with East London Cemetery, which is over here, although many's the time that mistake has been made and people have turned up at the wrong cemetery, sometimes as the guest of honour. But we're here at Tower Hamlets Cemetery Park, and it came to my attention through this little book produced by Doreen and her daughter Diane Kendall from the Friends of Tower Hamlets Cemetery Park. They were looking at people who were buried there with a seafaring connection. And amongst those is Edward Wood. Not this chap, that's Edward Wood, but Edward Wood. Edward Wood was a sea captain, and at the time that we become acquainted with him, he's just been put in command of a brand new ship just off the stocks on her maiden voyage. But many people are of the opinion that he's been handed a lemon. This is the ship, the John Bowes, and this is the illustration from the Illustrated London News, August 1852, of the John Bowes in the collier dock of the East and West India Dock Railway. The John Bowes was the first steam collier, or at least that's how we remember her. Technically, she wasn't quite the first. There had been another ship before her, the SS Bedlington, March 1841. She actually carried complete wagons of coal which could be rolled on board. That at least made sense. The John Bowes did not make sense, and that's why there was considerable skepticism. The John Bowes was built at Jarrow-on-Tyne by Palmer Brothers, and she was launched to skepticism on the 30th of June 1852. Let's have a look at why there was such skepticism about such a ship. We have the figures for that period. These were the British coal fields, and the London Coal Exchange just had a new building. This is the model. And from the records, we know that coal delivered to London from Northumberland and Durham was 3.5 million tonnes per year. That was more than all other cargoes combined. A sailing collier could carry about 300 tons by the mid-19th century. They made a maximum of around 9 trips per year. We'll see shortly why that was. These are sailing colliers. You may recognise the location in the Regent's Canal dock. How many ships were required to carry 3.5 million tons of coal a year between Northumberland and London? Well, if we divide 3.5 million by 300 and making 9 trips, we come to about 1,300 ships. Well, let's say they only made 5 trips a year each. That gives us about 2,350 ships. Worst case scenario, that rather than carrying 300 tons, they only carried 250, well, you might get away with 2,800 sailing ships. The actual figures, and we have them for 1848, which is pretty close, there were 3,000 sailing colliers just on the run between Northumberland and Durham and London. They were making 12,000 round trips per year, so an average of only 4 trips each per year, and an average of only 290 tons per vessel per trip. A sailing ship would cost you about £200 new. A steamship would cost you £1,200. Okay, she could carry perhaps twice the cargo. Therefore, for your £1,200, you could buy 1 steam collier carrying 600 tons, or 6 sailing colliers carrying 1,800 tons. Well, go figure, which would you prefer? And that was one of the reasons why there was considerable skepticism about ever bringing out a steam collier. The John Bows had departed from Sunderland on the River Wear at midnight, 27th to 28th July, so very soon after her launch. She'd arrived on the 30th of July at the collier dock Blackwall after a trip of 2 to 3 days. Well, impressive, but that's what a steamship did. Now, where was this collier dock at Blackwall? It was here. I hope that some from Poplar Dock Marina are watching this evening. This is where you live. And it was here. Just there. We'll have a closer look. The West India docks had been commenced in 1800. By 1802, the import dock here, together with Blackwall Basin, which was where the ships would come in, that was open. 1805, the City Canal opened, followed in 1806 by the export dock and Limehouse Basin at this end. Yes, there was an earlier Limehouse Basin. That's where the lighters came in. And originally on the plans, there was to be a reservoir next to Blackwall Basin, which would be used to top up the reservoir with clean water. But as you can see, in William Daniel's famous painting of the West India docks, no reservoir is shown. Now, his painting contains much which is apocryphal or at least wildly inaccurate, not least the houses along here. If we look at this more accurate painting, you can see there was absolutely nothing along that end, but certainly no reservoir. But that came later. In 1828, the reservoirs were at last dug for Blackwall Basin, 2 of them side by side. In 1838, the London and Birmingham Railway opened. Euston, Rugby, Coventry, Birmingham, 112 miles. The engineer was Robert Stevenson. It's now part of the West Coast Main Line, the southern section. In 1843, the two reservoirs were made into a single timber pond. They'd found it was actually more efficient, more cost-effective to dredge Blackwall Basin, so they just turned the two reservoirs into a timber pond where timber could be kept to season. 1846, the London and Birmingham Railway and the dock companies asked Henry Daniel Martin to lay out a line connecting to the West India docks for goods only. And that was the East and West India Docks and Birmingham Junction Railway. In those days, if you were setting up a company, you wanted your potential shareholders to know what the company was about. You wouldn't call it something like consignia. That would be silly. How would they know what you did? And also in 1846, the London and Birmingham merged with others to form the London and North Western Railway. 1851, the East and West India Docks and Birmingham Junction Railway bought the Blackwall Basin timber pond to create their railway dock for the import of coal. And there it is. And they changed their name in 1853 to the North London Railway. So that's where this railway dock was. The John Bows got back to Tyneside on the 3rd of August 1852. So the total trip had been 6 to 7 days. Okay, well, she was a steamship. That's what you would expect. But hey, she hadn't been carrying any cargo, surely. It would have been impossible to discharge the cargo. Why was it impossible to discharge the cargo? Let's have a look at how it was done. It was done using these guys, coal whippers. And what they did was to climb up this thing, and this is my first question for the audience. I'm hoping that somebody will be able to tell us what this thing was called. All the pictures of coal whippers show them, 4, sometimes 3 of them, climbing up this thing that looks like a ladder or trestle, and then jumping off it, using their combined weight to whip the coal up out of the hold of the collier. Did they have whole teams of them? No, because you only had one hold on a collier, and it was tiny. This is a well-known collier, the Earl of Pembroke. She became His Majesty's bark Endeavour. So there was a limit to how fast you could get the coal out of a collier. So for each ship, to load the coal would take, let's say, 7 days. Your outward trip would take 7 days. To take the coal out would take 7 days. And here is one of our colliers, clearly with the coal having been taken out, but she can't go anywhere. You can see she's about ready to roll over because they've got to put the ballast back in. Now, they wouldn't have to actually load her down to the gunwales, let's say 5 days to put the ballast back in. The return trip, 7 days. Unload the ballast when you got back, another 5 days. So the total trip was going to be just under 6 weeks. That was why a collier would make a maximum of 9 trips a year, typically only 4 or 5. So the John Bows could not possibly have unloaded her cargo and set off again. But she had. She had discharged 540 tons of coal in 18 hours and reballasted, which was absolutely astonishing. How had that been done? Well, incidentally, just to mention, that was 12 weeks' work in 1 week. Remember, she carried as much cargo as 2 sailing ships, and she'd done the whole job in a week. Well, have a look, first of all, at the length of her hold. Okay, that was about 60 feet. That's why the main mast was set so far back. Okay, so maybe you'd have got several groups of coal whippers round the hold. Also, she had water ballast. Now, that was practically a first. So that would have allowed her to reballast in a matter of, gosh, an hour or so, rather than several days. But still, how on earth had she managed to unload her cargo in that very short time? What else did she have up her sleeve? To find the answer, we need to have a look at this bit of kit, which some of you may remember from school days. It's called a set of Pascal's vases or water level apparatus. You may possibly remember that what you did was to fill it with a bit of water. Put a bit of food colouring in the water so you can see the water, and you carried on filling. And what happened was that the water rose to the same level in each of these different shaped arms. And that raised three important scientific questions. First, is that all it does? Second, what else did you expect was going to happen? And third, how much did we pay for this thing? About £40 these days, in case you're wondering, and very few schools probably have one now. But let's simplify it for a moment. Let's consider just these two arms here. Let's make this arm slightly shorter, and let's top up this side as fast as we can. Well, what's going to happen is it's going to spill out on this side. So far, so very obvious. But let's suppose that you are an Aquarius, a Roman water engineer, and you are in charge of building the new HS3 aqueduct. You've got your water as far as this side of the valley. How are you going to get the water across to the other side of the valley? Well, you could do it like that, and it was often done like that, with an aqueduct like that, with a very slight slope, an extremely slight slope. The Romans tended to build them with a gradient of about 1 in 3,000. So the aqueduct would drop about 50 feet in 30 miles, 15 kilometers in 50 kilometers. Those aqueducts that survive often look like this, an open trough. In fact, most of an aqueduct, any aqueduct, was normally underground. We only see the bits left above ground. And in fact, they were, even the parts above ground, were normally covered over with a dust cover like this to keep out animals and dirt. And they did it like this. How did they get their 1 in 3,000 gradient? They used this thing, which looks like a wallpaper pasting table, but it actually contains a little slot with water. And so they could get the correct angle as they built the aqueduct. So let's suppose that you were to run your aqueduct down the valley and up the other side and let the water into it. What you would end up with would be a very large puddle or a small lake, and you would receive a severe reprimand from the general manager. But let's suppose instead you used an enclosed pipe like this and ran it down the valley and up the other side, let the water in. Then what would happen would be that the water would, as if by magic, run down one side, up the other side, and carry on. You wouldn't do it like this, you would do it like this. And you can see that, in fact, the Romans used very substantial pipes, more like that. And so if you come across a bit of Roman aqueduct with a slope on it, don't necessarily assume that the water was running down the slope. It might just as easily be running up the slope. They knew what they were doing. Let's have another look at our Pascal vases. Let's take a slightly more elaborate version. You would never use one like this in a school. It wouldn't last 5 minutes. And let's fill it up with water part way. And let's bring in one of these guys. Oh, look, here comes another one. And let's send them down into the pipe. We'll now send them down the pipe. As this guy swims down, he is experiencing a greater water pressure. As this guy goes down, he also is experiencing more pressure. They are both now at the same depth measured vertically. They are both at the same pressure. And even if we make this pipe here much wider, so that there's much more water above this guy on the right than the one on the left, they are both still at the same pressure. If we put an Olympic swimming pool on the top of the other guy, believe it or not, and this is where it becomes not necessarily intuitive, he is still at exactly the same pressure as the guy on the other side, because they are both at the same depth measured vertically. Send this guy down to the bottom of the pipe, he is now at a higher pressure. They are now at the same pressure. The guy that worked all this out was Blaise Pascal. He lived from 1623 to the sadly young age of only 39. You might be surprised that he lasted as long as he did, because he liked to do this sort of thing in the days before health and safety. What he is showing is that simply with a pipe into a barrel, and maybe he climbed a very tall ladder, maybe did it off the top of his house, but that was sufficient to burst the barrel. That's why the Romans had to use such very thick pipes, like that. Let's now seal our divers in. Don't worry, they've got air tanks, they'll be fine. And if we now put a plunger into the tank, we can push in on that plunger. That will increase the pressure of the water. We're not compressing the water because it's virtually incompressible. But if we increase the pressure, that increase in pressure will be transmitted throughout the body of water. Yes, there's a difference in pressure from top to bottom, but wherever we push in, then that difference in pressure, the same difference, will be transmitted equally throughout the body of water, wherever we put the plunger. And that again was all worked out by Blaise Pascal and is expressed in Pascal's principle or principles. Exactly which bit he worked out within his own lifetime is a moot point. But essentially, a pressure change at any point in a confined liquid is transmitted throughout the liquid such that the same change occurs everywhere. Pressure exerted on a liquid in a container is transmitted undiminished to all parts of the container and acts at right angles. Pressure applied to any part of the enclosed fluid will be transmitted equally and instantaneously in all directions. The change in pressure is due to the weight of the fluid, therefore the pressure at given elevation depends solely upon the height of the fluid column measured vertically. And that's all you need to know for this evening. Blaise Pascal didn't do very much by way of exploiting his discovery, but we understand that he devised this thing here, which looks like a musical instrument, but essentially what he found was that a weight of 1 pound, 1 kilogram, 1 ton, call it what you will, across an area of 1 square inch would balance a weight 10 times as great across an area 10 times as great. But he called it Pascal's hydraulic machine for multiplying forces, so it was a bit more than just a weighing machine. Remarkably, nobody seems to have done anything with this invention until nearly 150 years later. And we come to this guy, Joseph Braemar, who managed to patent a hydraulic press. Now, what he was saying was that if you push down on this side for, say, 10 inches, 10 centimeters, then this side will go up by only 1 inch, but you can raise 10 times the load. And he got a patent for a hydraulic press. And indeed, that's essentially how the old-fashioned hydraulic drum brakes work. But hang on, you're thinking, how did Joseph Braemar manage to get a patent for something which essentially had been invented 150 years before? This diagram appears in textbooks, sometimes to illustrate Braemar's press, sometimes to illustrate Blaise Pascal's invention. The reason seems to be that in reality, what would tend to happen is that if you actually push down on one of these things, the weight is just going to squeeze its way past, isn't it? The water is going to make its way past. In order for this thing to work, you have got to have a very reliable seal for your plunger. And the sort of seal that you have on an ordinary hypodermic syringe, which we're all looking forward to having plunged into us in the very near future, that just would not be sufficient. In order to cope with the sort of pressures involved, you've got to have a very much more effective seal. And this was the seal that was devised, a seal whereby the pressure of the water would actually force the seal more closely sealed. And this was devised by this young man, as he was at the time. He was only 24, and he was Joseph Braemar's workshop manager at the time. Now, this is the well-known drawing of Henry Maudsley. If anyone can find me a picture of him as a younger man, that would be more appropriate. But it's thanks to Henry Maudsley that Joseph Braemar's hydraulic press and everything else that we're going to look at this evening could work. Without this reliable seal, the hydraulic press could never have worked. But Braemar got a patent for it. And the hydraulic press illustrates the important scientific principle of tin staffel. There is no such thing as a free lunch. Yes, you can lift 10 times the weight, but you have to push down 10 times as far. This was a hydraulic press made by Braemar's sons and was in use at the Ordnance Survey until around 1970. If you've got an old Ordnance Survey map in your loft, it was probably made on this press. Joseph Braemar very quickly went on to invent, credit where credit is due, a hydraulic crane. You had a simple hydraulic ram with a rack and pinion. The ram went up and down, the pinion went round and round, and your load went up and down on the crane. But it was very limited as to how much travel you could get on the crane. At just the same time that Joseph Braemar was developing his hydraulic crane, the same year, a fight broke out in this building in London, the Royal Institution. The director of the Royal Institution was the Professor of Chemistry, Sir Humphrey Davy, and the instrument maker, John Newman, had been injured. The lab technician, William Payne, who'd punched him, was sacked, and Humphrey Davy found himself without a lab technician. And he gave the job to this young man, son of a blacksmith, apprenticed to a bookbinder who had been attending his lectures. It was, of course, Michael Faraday, aged just 21, got his first proper job washing test tubes in the basement of the Royal Institution. Whilst Michael Faraday was getting his feet under the workshop table at the Royal Institution, the Regent's Canal was getting its enabling act and starting digging. And it took some 8 years to complete, as I'm sure we all know, and was opened officially on the 1st of August 1820. This is where I'm going to just pop across and have a look at the very fine plans which Malcolm Tucker and Tim Smith produced for us. When I did my original talk on the Regent's Canal, I made up my own plans, but based on these, I thought this time I'd give credit where credit's due and show Malcolm's plans. I hope he won't mind. Here's the lee navigation coming down to the Thames. So in 1820, the Regent's Canal dock opens just this little bit here, with its ship lock going out to the Thames there. That's all we had in 1820. We'll come back there later on. In the same year that the Regent's Canal dock opened, this gentleman, Hans Christian Ørsted, discovered the connection between electricity and magnetism, noticing that an electric current caused the needle of a compass to divert. Put the wire across there and nothing happens. Put the wire longitudinally and the compass needle goes that way. Put the wire underneath, the compass needle goes that way. Put the current in opposite direction, the needle goes that way. Put it that way, the needle goes that way. And Ørsted had no idea what was going on when he published his discovery. And it was not until a few months later that this guy, André-Marie Ampère, worked out what was going on, that the only possible explanation was that you had forces going in circles, which was absolutely unheard of. Michael Faraday would go on to do his own version of the experiment, and for the very first time would produce continuous motion with this wire dipped into mercury. Again, no practical application at all yet. And you can see the actual apparatus if you visit the Royal Institution. We go now to Newcastle, a town in the extreme north of England near Newcastle, and to this young man. And he was some 19 years younger than Faraday. And he was an extreme sports enthusiast. He was a participant in the most dangerous leisure activity that man has ever devised. Of those who drown, far more drown each year, not at sea, but on our inland waterways, often doing this. I was scarcely ever away from the waterside and fished from morning till night. They used to call me the Kingfisher. So said William Armstrong. And he liked to get right into the water, like this, and he would have become well aware of the power of water, not only to knock a grown man off his feet, but to move boulders. Now, if you're the user of a well-known operating system, you may recognize this picture. Before Martin has apoplexy, I'm sure that if I say to everyone, you should all be using Microsoft Windows, then Bill Gates won't mind us using his photograph. It's actually of an old water mill in Valais in Switzerland. Let's pretend for the moment. Oh, and sorry, one thing I should explain. It looks like a Oh, a very artificial bit of kit, doesn't it? It looks purely for the tourists. Surely that's not a real water wheel. And hey, how's the water getting to it? It's running up this pipe. Well, we now know that it doesn't necessarily have to be pumped up that pipe. If the top of the pipe is somewhere further up the hill, yes, the water would very naturally run up it and operate the water wheel. But it does look very, very touristy to me. But okay, let's for the moment pretend that the water wheel is actually on the River Dee at Densdale in the Pennines, and it's 1835 or 36, we're not quite sure. William Armstrong would have been 25 or 26. And he is on a trout fishing trip. And he's looking at the water wheel and thinking to himself, wouldn't it be more efficient if the water were carried in a pipe and applied directly to the wheel, which was sealed? And here we're using a little GIF that's been produced by Bill Todd. This is the machine that William Armstrong devised in 1838. And this, I believe, is in the Museum of Science and Industry in Newcastle. I paid one visit there many years ago and would probably have walked past it without knowing to look for it. So if anyone can confirm for us that it's still there and you can still see it, then that would be very useful. This is the actual machine. And if I may, I'll just make one little modification to Bill Todd's GIF. What we need to do is to seal that bit there, because the whole thing was sealed. And it went round like the clappers. Now, Armstrong could find no interest in his device, but it was a remarkable invention, and it has a commemorative plaque at High Bridge. William Armstrong's water-powered rotary engine was built here at Henry Watson's works, 1838. Armstrong employed 25,000 people at his Ellesmere works. They would follow just shortly after. This was his factory on the Tyne. And to inventor, engineer, scientist, and businessman, we must, of course, also add arms manufacturer, but his first gun was still a few years away. And we're coming up to about halfway through the talk, which is fine. I'm going to have a little pause in a few minutes. We're just about on schedule. Now, Armstrong could find no interest in his first version, and he would go on to develop this reciprocating or oscillating water engine. But somehow the original one, I think, has a certain simplicity and elegance to it. Now, Armstrong would first come to prominence, not through, well, that's my alarm going off to tell me we're coming up to halfway through, so I'll just go a little bit further. He'd come to prominence not through hydraulics, but through this invention here. The Cramlington Colliery Railway ran from the colliery up Sedge Hill and back down to the Tyne. And in 1840, a engine man was adjusting the safety valve here and got a tingling in his fingers. And over the course of the next few days, he found that he could get more and more, not a tingling, but a shock. And if a whole lot of his chums joined hands, they all got a shock. And a number of different people investigated, including William Armstrong. He actually corresponded about it with Michael Faraday. And what he built was this device here, steam coming out of these nozzles, impinging here and actually generating electricity. He hoped to make more of it. It was essentially the first effective generator of static electricity until the Wimshurst machine came along years later. But it was because of this discovery that William Armstrong was actually elected a Fellow of the Royal Society. and among his sponsors were Michael Faraday and Charles Wheatstone. Who was Charles Wheatstone? Let's have a look. The very first commercial use of electricity anywhere in the world for any purpose was here at Limehouse. On the London and Blackwall Railway, this was the stationary winding engine at the Minories, where Tower Gateway now is. And here was the Oyster card reader. It's actually a single version of these, where the needle telegraph, which we saw a few moments ago, had now been applied by Charles Wheatstone and William Cooke. And we can see here 5 of the stations on the London and Blackwall Railway. A very simple application of electricity, but the first commercial one. They did actually experiment with pointing to letters, but that needed more wires. Just the single pair of wires, a simple binary stop, ready, on, off, yes, no system, years ahead of its time. Now, at just the same time, this guy had launched his ship, the Great Britain, Isambard Kingdom Brunel, a very close contemporary of Armstrong. They were 4 years apart. This guy, Robert Stevenson, a friend to them both and very close in age. And this chap, James Meadows Rendell, slightly older. I could pick many others, but these are the ones we're going to look at later on. Now, this is where we're going to have our pause in just a few moments. William Armstrong devised his first hydraulic crane in 1846. Now, looking at that picture, you couldn't possibly tell how it worked. But this one, from the patent application, gives us a better idea. There's some sort of mechanical gubbins here lying under the ground. You can see there's a plate there. And it looks like some sort of pulley system. Here's another version. Now let's assume for the moment that it is some sort of a pulley system, and let's remind ourselves of how pulleys work. These are the type we had in school, and we tended to put the pulleys, the sheaves, one above the other so we could see what was happening. And you may remember that if you pulled down on this bit here, you could lift 4 times the effort that you were applying, but you had to pull through 4 times the distance that the load went up. Again, tin staffel, there is no such thing as a free lunch. What William Armstrong devised was exactly the same idea, but working the other way around. Rather than pulling on the chains, you were forcing the 2 ends apart. Armstrong's cylinder, ram, and multiplying sheaves, or the hydraulic jigger. And I think the very best example you can find is at the old Millwall Dock entrance. You can actually go and climb all over it. And depending on your luck, it may or may not have been recently painted when you get there. So here it is. In this particular case, you can count 1, 2, 3, 4 lengths of chain. And in this particular case, because it's a big one, the sheaves at this end are being carried on this little railway track by this wheel here. But essentially, you're forcing apart the 2 lots of sheaves, and that causes the chain to move, in this case, 4 times as far as you move the sheaves apart. You will find a very good explanation of how Armstrong's hydraulic crane would have worked here at St. Catherine Dock. Now, this is actually a later example, but it really shows how it was applied to a crane. There's the hydraulic jigger in its entirety being used to lift the load. And you can see in this case, you've actually got 8 lengths of chain. And you've got another pair of jiggers just to the side here, and they're used to slew the crane back and forth. So you've got one to do the lifting and another pair to do the slewing. And I'm assured that this used to actually work when you press the button, but it hasn't actually run for many years. If anyone can remember pressing the button and having it work, do please put that in the feedback. And in this particular case, it was an 8-to-1 advantage. That was about as far as they ever got before there was too much slop. That's one at St Catherine Docks. And that's a further development. Now, this is where I think we'll have a little pause here now, Martin, just in case anyone's given any feedback so far. Otherwise, I'll carry on after a few moments. You just need to unmute there, Martin.
Sorry, right. Yes, Jeremy, we don't have any questions as such in the questions and answers. So if anyone would like to ask an intermediate question that won't wait until the end, then do type it in now, or else we'll move on.
That's fine. Yes, well, I'll just carry on for the moment then. And if anyone does...
I should just give them a moment.
Yeah, give them a moment,
type,
sure.
Because they perhaps can't type quite that fast.
That's fine.
Somebody, Catherine, has said, great talk, and it says it's pronounced Sedge Hill, by the way. I'm not sure.
Oh, thank you. Sedge Hill.
Sedge Hill.
Oh, it's Sedge Hill. Thank you.
I can't remember how you pronounced it now.
Nor can I, but I nearly always make a terrible howler on pronunciation.
Someone says seg like egg. Oh, so that's Catherine again.
Ah,
Seg Hill.
Seg. Right, I'll write that down before I forget.
Right. Well, apart from the pronunciation issues, we have no specific questions. So
that's fine.
Let us progress.
I'll press on. Now let's get this out of the way. That is a thumb. That is a square inch. That is a pound. That is a pound per square inch. It's a good, honest, practical measurement that anyone can comprehend and visualize. A newton is the force required to accelerate an object with a mass of 1 kilogram at 1 meter per second per second. A pascal is a pressure of 1 newton per square meter. That is a wet paper bag. A pressure of 1 pascal would not even dent it. It is a useless measurement. Before we even know they're there, we have to have 100 of them, a hectopascal. To do anything practical, at least 1,000. And to do any serious engineering, you've got to have at least 1 million. But that's SI units for you. Coherent, but silly. 100,000 pascals, 1,000 hectopascals is 1 bar. 1 millibar is 1,000th of a bar. 1 standard atmosphere is that. Meteorologists, depending on the nationality, talking hectopascals or millibars. Plumbers talk in bar. Doctors talk in millimeters of mercury. To a doctor, a pascal is something they give you to suck when you've got a sore throat. Now, having got that out of the way, we can now move on here. This is the reservoir that William Armstrong had to play with in Newcastle. We can see here elevation 300 feet there, 350 feet there. Oh, yeah, 450 feet there. So, okay, the reservoir wasn't quite at the top of the hill. Ideally, if he built a reservoir at the very top of the hill, it's a simple calculation, you multiply by 0.434, he might have got as much as 195 psi. Typically, in the mid-19th century, water pressure was between 40 and 70 psi, but in Newcastle, you got 90 psi. Having a shower would have been quite invigorating in Newcastle in 1849. Now today, typically the water pressure from our taps is between 3 bar and 7 absolute maximum. Your dishwasher manufacturer would be worried if you had more than about 80 psi. Now, how was William Armstrong going to bring to the people of Grimsby the same sort of pressure that he could get back home from his bathroom tap? This, of course, was at sea level. Well, this is what he did. The engineer in charge of the new Royal Dock at Grimsby, that was begun in 1846, that was this guy, James Meadows Rendell. Remember him? We saw him a few moments ago. He was the engineer in charge, a friend of William Armstrong. And so Armstrong was able to suggest that they used hydraulic cranes at Grimsby, but how were they going to get the pressure that was needed? What they devised was this, and here I'm very thankful to Malcolm Tucker, and particularly he put me in touch with Tim Smith, and Tim was able to produce this very nice, clean, clear version of the plans for the Grimsby Docks Tower. And depending on which article you look at, it's very hard to find how tall was this thing. Well, the plans show it was 200 feet to there, it was another 100 feet to there. So it was 300 feet in total. But what it contained was nothing more than a water pipe. And you can see the water pipe went up just above the 200-foot level. And on the top was a header tank. Now, how come there was a header tank? How did you get to the top of the tower? That's the thing that's really hard to find out, but thanks to Tim, he found this part of the plan which shows it was a hollow tank. You could go through the middle. Now let's say that it went another 8 feet or so above the crenellations here. So multiplied by 0.434, that would have given you 90 psi at the bottom of the tower. In other words, this tower would give Grimsby Docks the same pressure that William Armstrong could get back home from his bathroom tap. But that was the only way they could do it. It's still there today. You can go up. I haven't, but it's now on my bucket list. Now, when Malcolm Tucker and Tim Smith and I were exchanging these photographs, and we were trying to figure out, what are we looking at here? Are we looking horizontally through a corridor? No, this is looking, I think, down rather than up. It's looking down the tower. This is the water pipe. That's it. That's all that the tower was constructed to contain. I think this one is probably the electric cable. What's this bit here, swathed in health and safety wrapping? Well, that, of course, is simply the spiral staircase. That's how you got up it. The reason it's swathed in health and safety wrapping is that if you were at the bottom of the tower, one of your mates leaned out with their iPhone to take a picture and dropped it, well, here's a exercise for those of you who are school teachers. You work out, it's about 200 feet. How long would it take for the iPhone to reach your head? how much of a dent would it make in your head when it hit you? That's why it's wrapped in health and safety wrapping. So here is the spiral staircase coming up. You go up a little straight staircase and out, so you're standing inside what would have been the water tank. The pipe is just underneath there, coming up into the tank. It was novel, grand, captivating, impressive. It was only after they'd started to build the thing that William Armstrong realized that it was novel, grand, captivating, and completely unnecessary. The one on the right would not just do the same thing, but would do it very, very much better. How so? Here's our water pipe at ground level. There's a vertical pipe. Now, we've already established that no matter how much water you put on the top, it's going to make no difference at all. You're only going to get the pressure dependent upon the height of the column of water. Okay, let's just forget about the column of water. Put a ram on top of it. Let's now sit our tank of water on top. You're now getting the full benefit of this tank of water pushing down on the little bit of remaining water in the column. Well, rather than having it wobbling round on the top, why not enclose it in a sleeve like that, encircling the ram? Whilst you're at it, why not put something heavier rather than just water, fill it with gravel or iron, like this. The only bit you've got to worry about, remember this is just a hole here, the only bit you've got to worry about is this bit here. This is the bit that you've got to seal, and you're going to use Henry Maudsley's wonderful seal, which is pushed tighter by the pressure of the water while still allowing the ram to move. It's going to be leather. Hydraulics was not a job for vegans. The weight is going to be 94 tons. I'll tell you in a moment how we get to that. And that will give you not 90 psi, but 700 psi at the bottom. What William Armstrong had devised, and he did it around 1850, the first one was built in 1851. So in other words, whilst they were still building the thing at Grimsby, the weight-loaded hydraulic accumulator. It was first actually installed 1851 here in Liverpool. The dock engineer was this guy, Jesse Hartley, and he designed the very nice castle type towers around. But look at this one at the back here. Does it look strangely familiar? Yes, this was the tower that Jesse Hartley apparently designed in order to receive William Armstrong's hydraulic accumulator gubbins. It is octagonal. And the one that we have at Limehouse, which is, nearly 20 years later, we say it's unusual. Yes, it's unusual, but by no means unprecedented. It's practically a copy of the one from Liverpool docks. There it is. And the cylinder is 25 foot, so the pressure from the water alone would be only about 10 psi, negligible. The ram has a diameter of 20 inches, so working it out, it's about 314 square inches. The working pressure we want at the bottom is 700 psi. Therefore, that works out at about 0.3 tons per square inch. Therefore, do the maths, the load spread across the ram is going to come out at about 95 tons. The weight case moves up and down like that. That's its stroke. And the tower, in this case, is octagonal. Just in case, and this isn't often quoted, the actual amount of water in the tower is only about 390 gallons. It's not that much. There's not that much water in an accumulator tower. Its purpose is to regulate the pressure. They could generate 700 psi with a steam pump, no problem. But as you started to use your water at 700 psi, you didn't want it to drop off as soon as somebody operated a crane or a capstan or a lockgate or a bridge. You needed the pressure to be maintained all around the site. So what you had was one or more of these accumulators. They could very quickly, within a matter of minutes, be pumped up again by your steam pumping engine. That's the plaque, which was sadly stolen during the metal theft era, but we do have a copy there preserved. Now moving on, and we're doing all right for time, I think. So the weight-loaded accumulator, there's the Grimsby Docks Tower. To give 700 psi at the bottom of a tower, it would need to be over 1,600 feet tall. Like that. In other words, 8 times the height of the one at Grimsby. Now, you'd have a very nice column of water. You would hardly need to bother to put a header tank at the top, although you could if you wanted to, but it might wobble around a bit. But astonishingly, this one at the bottom gave you the same thing, 700 psi. Now, it will come as no surprise, you probably guessed by now, how did the John Bowes unload 640 tons of coal in 18 hours? Well, it did it using hydraulic cranes. Now, our artist is giving us to understand, I think we must conclude, that these are the hydraulic cranes. Now, you might well say, well, they don't look like hydraulic cranes to me. Now, I didn't think that this looked like a steam collier. I was quite convinced well, if that's a steam collier, my name's Frank Sinatra. But in fact, the artist was exactly correct. Believe it or not, that is the John Bowes, and that is the John Bowes in later years. We had these photographs. I couldn't believe that that was the same ship, but sure enough, it is. She was modified. They modified the stem, the bow, but that is the same ship. There she is as built, and there she is some 54 years later. So let's give the artist some credit and say that, yeah, maybe what he's showing is what the hydraulic cranes look like in the railway dock at Poplar. To me, they look a bit more like accumulator towers. Maybe he was drawing the wrong thing, but let's give him the benefit of the doubt. These don't look like any hydraulic cranes that most of us have ever seen, but again, let's give Gustave Doré the benefit of the doubt. They look more like something out of Doctor Who to me, but that, I think, is a fair impression of a hydraulic jigger sticking out the top there. And these are from 1872, some 20 years later. But that is definitely a hydraulic crane. That's one from 1892. That's one that was preserved at Bristol at least until 1970. And interestingly, they've actually preserved the bit of jointed pipe that allowed these cranes to be semi-mobile. This was, of course, their Achilles heel. You had to connect them to the water supply somehow, so they couldn't just go wandering all over the place. But they made heroic efforts to allow them to move within reason. Those are hydraulic cranes at Limehouse. We've got the actual date there, 1908. And those are definitely hydraulic cranes at Limehouse. But what the originals look like, we don't seem to be completely sure. I think a good time just to go back to the plans though, because we can have a look at what the first accumulator tower looked like at Limehouse. The barge dock there had been filled in there. We had the barge lock here, 1849, and they'd already started to extend the dock. This was the astonishing thing. They knew what was coming. They knew what they were doing. They were going to be ready. And they were already starting to connect up the Regent's Canal dock to the Lee Navigation dock. And our first hydraulic accumulator tower and pumping station was here, just behind the London and Blackwall Railway, just alongside the Commercial Road locks. And our thanks to Tom Ridge, who produced this very nice little drawing from, I think, the only photograph, well, the photograph he was working from was, I think, at Bancroft Road, and he's produced this very nice drawing. If he or anyone can let me see the original photograph, I'd be interested, but I think this drawing is fine. It shows us what it looked like. Quite a nice bit of architecture. We'll pop back to Limehouse. So how was it that William Armstrong was able to get his hydraulic cranes into Limehouse in the same year as they had them at Poplar? Now, Poplar Dock and the Regent's Canal Dock were bitter rivals. But hey, this was a guy who was quite prepared to sell guns to both sides in the American Civil War. It's what he did. That particular contract didn't go through, but he was an arms dealer, no problem at all, offering the hydraulic cranes to both sides. But how did he get them into Limehouse? I think we must assume through his mate here. James Meadows Rendell just happened to be the president of the Institution of Civil Engineers in 1852 and 53, and just happened to be a consulting engineer to the Regent's Canal dock at that time. And so it was, I think, that Armstrong was able to have his hydraulic cranes in place, not only in the railway dock at Poplar, but in the Regent's Canal dock, ready for opening. Now, in our remaining few minutes, I'll take you on a whistle-stop tour of some of the other surviving hydraulic artifacts that we have around the country and around the world. This one, I was surprised to find how early it is. I hope we all recognize it. It's the East India Docks hydraulic pumping station accumulator tower. 1857, surprisingly early, but I think this very nice architecture, it does look very similar to Tom Ridge's drawing at Limehouse. So that they didn't waste their efforts on producing, sorry, what I'm saying is they made a good effort at producing some very nice architecture. Yeah, there we are. Very similar, I think. They had hydraulic presses. This is made by Tangy Brothers. And when representatives arrived at the Tangy Brothers workshop at 40.5 Mount Street in Birmingham, yes, it was that small, it was that squeezed, they thought they'd come to the wrong place. They'd been sent out to every manufacturer of hydraulic rams in the country in order to help out this guy here, Isambard Kingdom Brunel, to get his ship, the Great Eastern, into the water. Tangy Brothers were by no means the only supplier of the hydraulic rams, but they would always claim, we launched the Great Eastern and she launched us. The Goole Civic Society have this bit of kit as their badge. This is the one surviving coal boat hoist at Goole. Now this is where Martin will have apoplexy, but I hope that the Goole Civic Society won't mind us using their video snapped from their video showing how the Goole coal boat hoist worked. If they do, we'll have to edit it out. But it shows how the Tom Pudding boats were lifted using hydraulic power. The whole boat tipped into the ship. In this particular case, the accumulators were right out in the open. The one that now remains, the accumulator, is in a tower, as we would expect. They had hydraulic lifts. And if you've been to Pontoon Dock on the DLR, you might wonder, well, what was the pontoon dock? It was this. A platform which wasn't just pumped out of water, but was physically lifted using this whole series of hydraulic rams. Now, in this case, they didn't need an accumulator because it didn't matter if it's going to take several hours to get the ship out of the water. You were only going to do it every few weeks. If you needed to do something on demand, quickly, available all the time, you would have an accumulator. It was here at the Victoria dock, before it was the Royal Victoria. You can see there, basin for hydraulic lift. And the guy that devised it, and I was surprised to find this, but we know his name, I think, at the London Canal Museum, Edwin Clark. We'll see him again in a moment. But that was the hydraulic ship lift at the Victoria dock. Just a view there of what Limehouse looked like at that time. Alan Faulkner very kindly allowed me several years ago, when I did my first talk on Limehouse, to reproduce the lovely drawings that Edward Paget Tomlinson did for Alan Faulkner's book, which I thoroughly recommend, The Regent's Canal, London's Hidden Waterway, available usually from the bookshop at the Canal Museum. We'll crack on. And of course, Edwin Clark, we probably know him better as the principal designer behind this one, the Anderton lift, which originally was a very elegant and simple design, just using a pair of balanced hydraulic rams, and they only needed the accumulator, which was just out in the open like that. They only needed the accumulator to just do the little bit of balancing at the end. And in balanced mode, it operated in about 3 minutes. But if necessary, using the steam engine, they could operate just one on its own in about half an hour. Hydraulic riveter there. I'm just going to not go on too long. This is one that's worth seeing at, you may recognize it, Ellesmere Port. And what you've got there is not only an accumulator tower, but one of the very few places where you can see one of William Armstrong's actual pumping engines. And if anyone can confirm whether they still steam it, I hope they do. That's at the Boat Museum, Ellesmere Port. This one was done by William Armstrong himself, mainly in order to clear the way for access to his Elswick works. There was a fixed bridge in the way, the ships couldn't get through, and he devised this fantastic swing bridge, the Tyne Swing Bridge, built 1873 to 76 by Armstrong himself, and still there to this day. Recently renovated, 2017 in all its glory. Definitely now on my bucket list for when I visit Newcastle. And you can, I don't know whether you can get in every day, but certainly when you're allowed in, this is one of the very few places where you can see Armstrong's original hydraulic engines still doing their original job. Now, if anyone can confirm whether they still pump, whether they still run on water, or whether it's now being converted to oil, I'd be grateful. There's no reason why they couldn't run on either, but they certainly still use the original engines, and they run at 49 kilograms per square centimetre. That is a horrible unit. You'll see it works out at 4.8 megapascals, or, surprise, surprise, 700 psi. It's always 700 psi. Why not just say 700 psi? But that's a lovely example of hydraulic engineering by Armstrong himself, still operating. As is this one, the Barton Swing Aqueduct, the first and still the only swing aqueduct in the world, but some 18 years after the Tyne Swing Bridge. There's its accumulator. Sir Edward Leader Williams was the designer. And it originally had a hydraulic press, the same as at the Tyne Swing Bridge. Most of the weight of the bridge was taken on a hydraulic press in the middle. So you're actually using the hydraulics to support most of the weight of the bridge. And yes, it swings full of water. Now I'm going to just, I think, skip over Cragside, but this was William Armstrong's house, and it was the first in the world to be lit commercially using light bulbs. Sir Humphrey Davy had devised the arc light, and William Armstrong had used in 1878 a single arc light, but he was the first to use the electric light bulbs devised not by Edison, but by the guy who'd got there before him, Joseph Wilson Swan. Even Edison would have to acknowledge Swan's precedent, and he had to form a joint company to work in Britain. And William Armstrong used Joseph Wilson Swan's light bulbs at Cragside in 1881. There he is. He's now age 68 by this time. And the bulbs were powered using hydroelectricity. But sadly, he had to go to a German inventor, Werner von Siemens, because already we were losing our preeminence in electric generators. Now I think we're coming to very nearly the conclusion. That one you'll see, you'll be surprised where that is. It's in the middle of nowhere, the Majestic Wine Warehouse. We actually get our wine from them at the Cruising Association, but it's the old pump house at Blackwall, and that was built for the Midland Railway Company, 1881. This one, we can't go without mentioning the London Hydraulic Power Company. They started off as the Wharves and Warehouses Steam Power and Hydraulic Pressure Company. As I said, in those days, you told your shareholders what you were going to do, but they, of course, became the London Hydraulic Power Company, which operated right up until 1977. That was their main pumping station, but we had this one in Wapping. And they had public power supplies in places you would not believe. Hull was the first, then London, Liverpool, then Melbourne and Sydney, Birmingham, Manchester and Glasgow, but surprisingly not Newcastle. And that's a lovely example showing that you didn't just need the accumulator towers, you needed your pumping engines and your boiler house. And that, believe it or not, was in Argentina, Buenos Aires. Now we're almost at our conclusion. We'll show here the 1898 pumping station. This is a view of Stepney Power Station, as it was in 1937, so we can date this photograph between 1927, when the coal jetty was built, and 1937 when the power station was done. We'll just have a quick look at Malcolm and Tim's plans again. So there's the 1869 tower over here. And we now bring in that picture there. And we'll bring in now Tim's plan on top of Malcolm's and merge the two together. That was how it looked in 1989. And we then lost these two corners. Oh yes, I wouldn't be forgiven if I didn't point out that the former Norwegian Seamen's mission is the former Finnish Seamen's mission. That was the only mistake, I think. And that's what Limehouse now looks like. And we're nearly there. And you can go all over the Surrey docks and see a wonderful collection of surviving hydraulic artifacts. If someone can tell me who it was that made sure that these were preserved, I'd be very thankful. The Surrey docks are probably the best place to go to see, oh, that's just to show, yes, the direct acting lock gate ram. Of course, we use the same at Limehouse, but using oil. The hydraulic jigger capstan, this is at Greenland dock, beautifully preserved. You would never guess what was underneath there, but they lifted one up to show what was underneath. The original simple hydraulic motors. And this example here, the very well-known Brotherhood 3-cylinder hydraulic engine. You wouldn't want to get in the way of one of those. The hydraulic jigger swing bridge actuators. There's one at Waltham Abbey. Hydraulic power very much safer than electric, of course. You could stick your steam engine on the other side of the site. That one there, which now has sadly gone from near Tower Gateway Station. That one, which is round the corner from where I live. And of course this one. I think this is where we'll conclude in a moment. You may not recognize that tower, but if I extend it a bit, you'll recognize, yes, it's here. And Tower Bridge was completed in 1894. And these were just the spare accumulator towers, the extras. It had 4 already in the towers. There's the building. And Baron William Armstrong, as he was, supplied the hydraulics. Now, here's a plan showing how the bascule goes up and down. If you visit Tower Bridge, you may come away convinced, as I must confess I was for years, Tower Bridge was operated by steam engines. I've seen the steam engines, they show them to you, they're wonderful. But these are steam pumping engines. The actual driving of the bascules was done by hydraulic power. If you are lucky and you go on a day when you're allowed into the bascule chamber, what you see is where the bascule is going to come down. What I don't think you normally get to see is the bit on top. And that was where they had a very simple system of 2 hydraulic motors each side, one big and one small, driving a simple pinion, engaging with a gear along the curve of the bascule. And this is what you see at the very end of the tour, This is one of the surviving hydraulic motors. This is what actually did the driving of the bascule. I think this is a photograph, someone may be able to confirm, of how it was originally installed, but I don't think they normally let you see where the pinion still engages with the rack. That's the bit I'd like to see, and I don't think you normally are let in there on a normal tour, but if someone has seen it, I'd be grateful. I think that's a good point, Martin, at which to call it a day. There's just one or two other bits I could show, but I think Tower Bridge is as good a place as any to conclude, and to thank you very much indeed for listening so patiently, everyone. You just need to unmute there, Martin.
Thank you very much, Jeremy. Now, I'm sure there must be somebody or a number of people in the audience with a few questions. So we have got time for a handful of questions. So if you would like to ask a question, please type it in the Q&A. Or are we all completely? If you feel you need to speak your question, then you can put your hand up using the one of the under more on my screen anyway.
I had literally only a couple of more slides, so I'll just run through them just in case anyone would like to see them, but we were very, very nearly at the end, so that's fine.
Yeah, no questions. I'm surprised that there would be no questions. I know it's working because one or two people have added remarks in them. Here we have a question from Seb. Was there a maximum practical range between an accumulator and its application?
Now, that's a very good question. If anyone can correct me, I'd be thankful. I should have brought my books with me. I remember looking at the various plans of Manchester, Liverpool, London. I know that they transmitted throughout London, the London Hydraulic Power Company, but I think a single pumping station, I guess you're looking at, what, half a mile or so? Would that be? I mean, the London Hydraulic Power Company, they did the whole of London, but they had a whole series of pumping stations around about. But certainly at Limehouse, it's surprising how little we had. I think at any one time, we probably only had one pumping station operating, but I would have guessed maybe half a mile or a mile or so. But if anyone can correct me, I'd be thankful. But looking at most of the plans, they were fairly localized in most cases, I think. But
thank you, Jeremy. Next point is simply a thank you from Ray Butler. Thank you, Ray. The next one is a question. Alan Gilbertson asks, the metals seem to be in good shape after so many years. Have you any idea why modern metals are more prone to rust?
That's a very good question. I think the answer is that they just used iron, didn't they? Probably wrought iron, which I don't think is particularly prone to rust. I mean, Brunel's Great Britain is still with us, only just. I think it was once we introduced steel and so forth, which might have been stronger. But the original iron, I think, did last fairly well. My understanding is that as long as you kept it full of water, you were okay. If the thing burst, you could be standing next to a hydraulic ram, and if it burst at 700 psi, you'd get wet feet. That was all, because there would be no actual explosion because the water was incompressible. But no, it's a good question. And I think the answer is it probably didn't really rust very much. They must have had to guard against freezing, although again, I understand that provided you kept the pressure on, it wasn't going to freeze. But if we have any metallurgists, I'm happy to be put right.
Okay, thank you, Jeremy.
Yeah,
we've got a few more questions, so I'm going to have to ask you to give some brief answers now.
Yep.
Nick Grundy asks, my boat has an Armstrong Siddeley engine from about 1955. Is the Armstrong Siddeley company connected with William Armstrong?
Yes, I'm sure. I'm sure it was after Armstrong's death. I think Armstrong, Whitworth. They eventually had to combine. They were bitter rivals, but had to combine. So Armstrong Whitworth, Armstrong Siddeley, Hawker Siddeley. Yeah, they are all linked historically. I'm quite sure of that.
Okay. And Alan Gilbertson asks, how did you charge people using a system over an area? Charge in the financial sense, I think he means.
Interesting. I don't know the answer to that. I generally don't know.
Okay. If anyone knows, perhaps you put it in. Perhaps you'll put it in the chat.
Yes, it's a good question, though.
Okay. Matthew Wood gives you a compliment, which you can read for yourself about how good the talk was. But he asks, how quickly did the number of coal ships reduce from the 3,000 that were running at the peak?
Now, that's an interesting one. Yes, I understand that the steam collier did catch on. Here at Limehouse, of course, we were sadly held back by needing a new lock. That's why we introduced the 1869 ship lock in order to keep up. But yes, I think the steam colliers did catch on pretty quickly and would have ousted the steamships because it was so much more cost effective once we had the hydraulic cranes to unload them.
Okay, I'm going to switch now to a couple of people who've asked to give their questions verbally. I'm going to start, because he's in alphabetical order, with Alistair. Alistair, you can speak.
Hello. Can you hear me?
Ask your question of Jeremy, please.
Can you hear me?
Yes, we can.
Yes, Jeremy, brilliant talk, wonderful images. You made a big point about the importance of good sealing on the hydraulics, and I wonder what materials were used to make the seals and what sort of life those materials had.
Thank you, Alistair. I am pretty sure, and I'm very happy to be corrected, I'm pretty sure they used leather. I think they always used leather. For all I know, they probably still do use leather in places where the hydraulic machinery is still going. I can't imagine what else you would use other than leather. That was why I made the rather naughty comment about not wanting to be a vegan if you were into hydraulic engineering. I can't imagine that anything would work better being continuously soaked and continuously under pressure and having to stretch and yet let things slide past. But if anyone can correct us, but I'd have said leather every time. Yeah.
Thank you.
Thank you for the question, Alistair. Right, I'm just looking to see if there was somebody else trying to ask a question verbally. I don't think there is. So we go back to the written questions. Couple of remarks there. I'm going to skip over the remarks rather than questions. And yes, there's one question from Peter Finch. Was the photograph of the Accumulator Tower near the old Hermitage, was that a photo of the Accumulator Tower near the old Hermitage entrance to the London dock?
Now I'm wondering which one that was. The one near the old Hermitage. I'm thinking that there's a pumping station there. I think maybe are we thinking about the impounding stations? There's certainly one there. I can't think of an accumulator tower near the Hermitage entrance, but there is certainly a impounding station, but I don't think an accumulator tower. But I'm happy to be corrected there.
Okay, just a couple of remarks from people. David remarks that LHP had 186 miles of mains driven from 6 to 7 pumping stations.
That's fantastic. Thank you.
Malcolm Tucker points out that mild steel rusts more readily than wrought iron.
Thank you. I'm so glad that Malcolm is listening. I was hoping he would be there and that he'd be able to help.
He's been here. And David Perrott points out that you can see hydraulics in action at the Kirkcaldy Testing Works, 99 Southwark Street. So I have to say that it's not open as long hours as London Canal Museum. Diane asks that she mentions that she walks the New River and there are several pumping stations. Are they the same?
Now, I would assume that they would be for water pumping, because I think the New River was essentially water supply, wasn't it? So I think they would have had water pumping stations. I wouldn't have imagined that they would have accumulators, but again, I may be completely wrong. Maybe they had hydraulic engines for water pumping. There's no reason why not. If ever you see a tall tower, odds are it did originally contain an accumulator. So yeah, you may be quite right that they were in fact accumulators, but maybe for the purpose of pumping the water along. But I may be wrong.
Okay, I'm going to allow one more verbal question, and that's going to be the last one, I think, from Nick Grundy, who obviously isn't a star of a Radio 4 a soap opera. Nick, you have Nick. You can ask your question.
I accidentally clicked the hand wave thing. I didn't have a further question. But
you don't have a question. Okay. All right. Thank you, Nick. Right. A number of people have expressed their appreciation.
Super.
And in various different comments. Brilliant talk, says Sally Ann. Interesting and informative, says Richard. And quite a number of other remarks on a similar nature. If you want to have a look at the chat, anybody, you'll be able to see things there. One more question, David Perrett. I'll allow one more. This really is the last one. David, would you like to ask your question live?
Yeah, good, very good. The pumping system in the buildings of the pumping system in Leith Docks, which are hydraulic as well, still survive quite intact. And there was also a very fine system that worked until relatively recently in Douglas on the Isle of Man. Oh. But I asked Tim Smith to give you more details.
Thank you very much, David. Thank you. That's very helpful.
Thank you for that. And with that, we bring proceedings to an end, because I think we've come to a normal finishing time for these talks. Jeremy, I'd like to thank you very much indeed for a superb talk, to quote from one of our audience, Alan Gilbertson, who puts it into just 3 words, which is excellent. An excellent talk. Obviously, a great deal of appreciation from the audience. A real tour de force of PowerPointery, as I might have expected from you, because I've seen one of your presentations before, and you are an absolute whiz with PowerPoint, and I do admire that skill that you bring to the piece, and obviously have a huge amount of knowledge about how there was a revolution at Limehouse. So I'd like to thank you all. Thank you very much. There is going to be a continuation, ladies and gentlemen in the audience, continuation of these talks, of course. We're going to continue with Zoom throughout January, February, probably March. Your guess is as good as mine as to when we'll be able to resume talks in the museum, but it will continue to be the first Thursday evening of the month. On Zoom, and it's just possible that we might do some kind of hybrid after we're able to resume in the museum, where we broadcast live from the museum. It's possible. So thank you all, audience. There's been a large audience tonight. Thank you all for taking part. Remember that the museum is now open again as from tomorrow, Fridays, Saturdays and Sundays, and will be open just after Christmas for 4 days. We're not on full opening hours yet. But after Christmas, we're going to be open for 4 days between Christmas and New Year. Do check the website for updates and for details of the future talks. Once again, Jeremy, many thanks indeed. And audience, if you'd like to do the applause in the way that I think you can raise a hand. And there we have a large number of people raising a hand.
Great. Thank you very much indeed for this.
Thank you very much, Jeremy, and everybody. Wish you all good night.